Before starting the video, I want to tell you about a platform I use a lot to learn what I teach on this channel. Skillshare is an online platform where you can learn a lot more about technology and many other things. I got a link. The first 1,000 people to register will have 30 days free to unlimited access for you to try and see for yourself. Go now, click the first link in the description or on the pinned comment. If you use my link, you'll be helping me a lot maintain the channel. In this tutorial, we're going to talk about security procedures in 4G. This video took a long time to do, so please like, share, and subscribe to the channel. When we subscribe, the operator sometimes provides a terminal, but it especially provides a communication service in the form of a SIM card. In 3rd and 4th generation, this card is called USIM, or Universal Subscriber Identity. However, we'll use the acronym SIM for Subscriber Identity Module because it is simpler and often used for the 2nd, the 3rd, and 4th generation. For the terminal to function correctly on the network, the SIM card must be present. It's obviously necessary to identify each SIM card or each subscription in a unique way. This is done by using an identity called the International Mobile Subscriber Identity. It is done to ensure that two random subscribers in the entire world never have the same IMSI. Its structure is hierarchical. It starts with 3 digits indicating the MCC code, Mobility Country Code, which is the country where the user is subscribed, which is generally where he lives. After that, the MNC Mobile Network Code, which is the code of the network in the country, then a number allocated by the operator. Two subscribers of the same operator never have the same number. The result is an identity of 15 digits maximum, which is unique throughout the world. The beginning of the IMSI therefore indicates to which country and operator the subscriber belongs. The IMSI of a subscriber never changes, unless he changes the operator, of course. This code is used when you move through the network. A 4G network enables the terminal to connect to the internet. All equipment connected to the internet must have an IP address to be able to send and receive data. In most cases, the IP address is not allocated statically. It is allocated at power up during a process called attachment. An operator can provide various types of services. For example, a public or professional access. During the attachment procedure, the terminal indicates the type of service it wants by specifying the APN, the access point name, which indicates to the network which P gateway it wants to use. Now, let's take a look at an example of how attachment works. When I turn on my cell phone, which is the terminal, it reads the SIM card to know the country code and the name of my operator. Assuming that I'm in the country where I subscribed, of course, the terminal searches my operator's network, listening to the beacon channels of the surrounding system. The operator's code is transmitted on each beacon channel. As soon as it finds the right network, it sends an attachment request message containing its IMSI. The message is received by the eNodeB and then transmitted to the MME. The MME checks if it has the subscriber's profile in its database. That's not the case here, because we are assuming that this is the first time I've turned my terminal on. The MME will then verify with the HSS if the subscriber is known and has access to the network. The HSS searches for the subscriber and transfers his profile. The message includes the APN access point name. Once the MME has stored the profile, it informs the HSS. We still haven't spoken about an IP address. An IP address is linked to a location. In this case, the IP address is linked to the P gateway. The choice was made by the designers of 4G networks. On one hand, to allow dynamic address allocation and, on the other hand, to leave this allocation up to the P gateway. The MME sends a message to the S gateway, which it resends to the P gateway. The P gateway can allocate an IP address. This IP address is then sent from the P gateway to the S gateway, then from the S gateway to the MME, and finally arrive at the mobile terminal. Let's imagine that I tamper with my terminal so that it sends the IMSI of my neighbor. I could use the network at his expense. The network must verify that when a terminal accesses a network, it corresponds to a valid subscription to a SIM card actually issued by the operator. This is the authentication mechanism. With a receiver set to the frequency of the base station, it is very easy to listen to what it transmits. A person with malicious intent could learn the information transmitted to me. This is enabled by the encryption mechanism. An attacker with a transceiver can very easily change the IP address that was allocated to me during the attachment procedure by superposing a signal on the one transmitted by the base station. To prevent this, a mechanism was developed that enables the recipient of a message to control the integrity of this message. When a terminal activates a service, it must identify itself. By default, the identifier used in the IMSI of an attacker listens to the exchanges of the radio bands and detects an IMSI. It knows which subscriber is nearby. Therefore, we avoid transmitting the IMSI. Instead, we use a temporary identifier which is regularly renewed. Authentication, encryption, integrity, allocation of a temporary identity are mechanisms which we'll see in this tutorial. This will bring us to look again at the attachment procedure, looking at how the security mechanisms are implemented. Authentication and authorization. How can the network verify that a terminal that attaches is given its valid identity? Each subscription is identified by an IMSI which is unique in the world. For each subscription, there is also a secret key. This key is stored both in the SIM and HSS. The key is 128 bits long, which gives 3 by 10 to the power of 38 possible values. It is more than the number of grains of sand of the earth. Practically, there is no chance to have two SIMs with the same key. When the user equipment attaches to the network, it sends its IMSI. To authenticate the subscriber, the network checks the presence of the secret key in the SIM card, without even transmitting this key on the radio channel. The method is based on a cryptographic function and a challenge. This challenge is simply a random number called RAND, coded on a large number of bits. Both the HSS and the SIM card make a calculation using the same cryptographic function, called F on this figure here. The F function takes as input the random number RAND and K, the secret key, and gives us a result. The terminal calculates the result and sends it to the HSS. The HSS compares the rest to the expected result, that is, the XRS calculated. If rest equals XRS, then it's interpreted as proof that the mobile terminal is in possession of the shared secret. So, if it really is the subscriber, the user equipment claims it is. The user equipment is authorized to communicate with the mobile network. If there is a difference between res and XRES, the user equipment is refused network access. The cryptographic function was specifically chosen because it's simple to calculate, using the rand and the key. In fourth generation, the random number rand and the key are 128 bits. The result of the function is a number from 32 to 128 bits. Knowing the random number and the result will not enable you to determine the value of the key. This is a one-way algorithm. If someone is listening to the values rand and res, he cannot deduce the value of the key. When a subscriber is abroad, it's still the HSS that generates the random number and determines the X-res. Both ends of the chain, the HSS, the SIM, are completely under the control of the operator. Each operator can define his own cryptographic function completely autonomously, as long as the sizes of the challenges and of the result conform the specifications. Note that a trusted third party can play the role of authenticator. The HSS just needs to provide the random number rand and the expected result X-res. It's the third party's responsibility to verify correspondence. In truth, the terminal interacts directly with the HSS. It's the MME that plays the role of authenticator. The terminal initiates the procedure by sending the IMSI to the MME via the eNode bay. The MME contacts the HSS. The HSS generates random number rand to pass to the terminal and expected result X-res. The HSS sends these elements to the MME. The MME sends the random number rand to the terminal via the eNode bay and waits for the response. If the terminal's result corresponds to the expected response X-res, the MME authorizes the terminal to enter the network. The rand X-res pair makes the base of what we call an authentication vector. The vector contains several other elements that we'll see later. Of course, once the vector has been used, we can't use it a second time. We've seen how the network authenticates the terminal. Nothing prevents an attacker from making up a fake base station and passing itself off a real network. With the procedures we've seen, the terminal has no proof that the challenge it received and that the response it sent weren't processed by a pirate network. That's why in 4G networks there is mutual authentication. That is, the network authenticates the terminal and the terminal authenticates the network. Let's look at how it works. We are still using the random number, a cryptographic algorithm G, and calculating a result that is called, in this case, an authentication token, AUTN. The authentication algorithm of the network in G is different from the authentication algorithm of terminal F. The token is therefore different from the result res. The HSS transmits the token as well as the random number. The MME sends in the same message, the random number rand and the authentication token, to the terminal. The terminal does its own calculations and verifies that it got the same value as the received token. If this is the case, the network is authenticated by the terminal and exchanges continues as we saw previously. If we apply this procedure exactly, there would be a major weakness. An attacker can just listen to the network and note the rand and the corresponding AUTN token. He then takes over the role of the network and sends the rand AUTN pair he has noted. Therefore, two successive authentications must lead to different results. So, we introduce a new input parameter called sequence number. The basic principle of sequence number is to increment the value of secret number with each new authentication. A part of the authentication token contains information about the sequence number. So, when you're receiving the authentication token, the terminal verifies that the sequence number does not have the same values as the last time. In other words, that the SQN is valid. If the sequence number is not valid, or if the authentication token is not the expected one, the terminal does not access the network. If everything's okay, the terminal computes the rest value and sends it to the MME. The MME checks that the rest is the same as XREST. After these challenges, the terminal and the network are mutually authenticated. The terminal can use the network. Of course, the sequence number should be incremented. A new authentication vector will have the new sequence number value. The use of authentication vectors is important because it enables a large flexibility in the authentication mechanism and in the network. So the HSS never communicates with the mobile terminal. It just receives an authentication request and responds with authentication vectors. All the protocol exchanges between the MME and the mobile terminal are hidden from the HSS and do not concern it. Another important point is the management of roaming situations. A foreign MME can ask the HSS for authentication vectors. Without having access to the secret key, the MME will then be able to authenticate the mobile terminal. In summary, in 4G networks, authentication is based on a secret key, cryptographic functions, and random numbers. The secret key is stored in SIM and the HSS. The secret key is never transmitted in the network. The SIM and the HSS makes the same calculations. The authentication is valid only when both find the same result. The authentication is mutual. The user equipment authenticates the network, and the network authenticates the user equipment. Ciphering and deciphering. In networks, ciphering is based on a very simple mathematical operation, which is XOR. In other words, the exclusive OR between the clear text and the sequence generated by the sender. This operation works bit by bit, so it takes one bit from every sequence and produces a bit as output. If the two bits are the same, the result is 0. For example, as shown in the slide, 1 XOR 1 equals 0. The operation is very simple to implement in hardware. In this example, the clear text is in blue and the ciphering sequence is in red. It should be noted that the sequence must have the same length in bits as the input data. To get the clear text from the ciphered data in green, you just need to repeat the operation with the ciphering sequence. This is one big constraint. The ciphering sequence must be different every time. If we use the same sequence several times, we completely lose all security properties. When we have a very large volume of data to transmit, we'll cut it into various packets and we'll try to cipher the packets with different sequences. The receiver must possess the same ciphering sequence in order to be able to get clear text. But how can we obtain a ciphering sequence of an almost unlimited size? We use an algorithm. Based on a few input parameters, generate sequences adapted to data ciphering. We start with a basic ciphering key that is relatively stable. It is conserved, for example, throughout a web session or during an entire communication. This shared key, KENC, is the basis of creating an almost unlimited number of ciphering sequences. The ciphering key is calculated from the number rand used for authentication and from the secret key. it is essential to use specialized functions that ensure that the string of sequences produced is the closest possible to random values. Because these are deterministic algorithms, if all input parameters are the same, the function will produce the same ciphering sequences as output. Because these are deterministic algorithms, if all input parameters are the same, the function will produce the same ciphering sequence as output. Therefore, we'll try to add elements known only by the sender and the receiver which change all new data sent. For example, we'll number each transmitted packet and integrate the packet number and the amount of data to cipher in the input parameter of the algorithm used to calculate the ciphering sequence. We'll also place a direction indicator, uplink or downlink, and a barrier number. The ciphering algorithm is executed on the mobile terminal on the E node B. The algorithm used must be standardized. An operator cannot define his own ciphering algorithm. All radio transmissions are ciphered, whether they are user data or signaling. Moreover, data exchanged between MME and the mobile terminal are ciphered by both sides. As for ciphering algorithms, there are several. Here, you see the three that are currently standardized in the LTE network or 4G network. The first, null, which does not cipher data, is to be prohibited and only used during network test periods. The second, Snow 3G, is an algorithm present in the third generation networks and the AES, which gives the strongest security guarantee at this moment. Each of the exchanges channels illustrated here can use a different ciphering algorithm. The ciphering algorithms and the cipher keys are negotiated during the terminal authentication phase. Now, here is an example to illustrate the different ciphering stages for an IP packet which contains user data coming from the internet. Let's consider a packet arriving at the PGW, which is then routed across the core network where it's guaranteed by the classic mechanisms of the internet world before arriving at E node B. Then, the E node B ciphers this packet before sending it on the radio link. We can imagine the following values are used to generate the key used to encrypt the frame: number of the packet counter between the E node B and the terminal, reference of the barrier, downlink or uplink packet, and size of the data to encrypt. The ciphering key negotiated earlier between the mobile terminal and the E node B during the authentication phase must also be specified. Upon reception, the mobile terminal uses the same parameters to decrypt the frame. The next IP packet will follow the same path, but in this case, the frame counter will increment by 1 and so. Even if it uses the same shared secret, a completely new ciphering sequence will be used. In summary, ciphering, also called encryption, is based on a stable encryption key ENC generated with secret key and the random number used during authentication. The ciphering sequence is specific to each packet. It is generated with KENC and parameters including a packet counter. Ciphering is based on exclusive OR. Ciphering and deciphering are the same operation. Integrity control. For example, I just received the message. How can I be sure that this message is coming from my network and not from someone else trying to send me false information, or that this message hasn't been modified by someone in the network? Now, We'll see the mechanisms put in place to ensure the integrity of data. The principle is simple. With each data frame, we add a code of several bytes of information. This code is calculated thanks to mathematical functions called cryptographic hash functions, and which have a few special properties. Knowing the output of the function, one cannot reconstruct the input data. Moreover, the size of the input data is always the same and does not depend on the size of the input data. The code added to each frame is called the Message Authentication Code, MAC. The authentication mark has nothing to do with the MAC layer on the computer. On the radio link, the sender adds this little mark to the useful data in each frame. The size of the mark chosen for the LTE network is 32 bits. The receiver is on its part, recalculates the mark from data and compares this code to the mark contained in the frame. If the two are the same, the receiver has the guarantee that no one has modified the data and that they come from the true sender. This is integrity control. Integrity control is used for signaling messages because they are critical. Now, let's take the example of a cell change order sent to the terminal. The handover command. If it's modified, the terminal could be sent to wrong cell and no longer work correctly or even cause disturbance in the network. The designers of 4G networks decided not to activate integrity control for user data. These data are not created by the network. If it's necessary, it's preferable to activate integrity end-to-end, that is, in the terminal application and on the application server. The receiver and the sender have the same hash function. They have the same key kint they negotiated during the authentication phase and which is generated in part of the random number and the secret key. Like the ciphering algorithm, the MAC, the receiver and the sender have the same hash function. They have the same kint they negotiated during the authentication phase and which is generated in part of the random number and secret key. Like the ciphering algorithm, the MAC sequence must be different each time, including when the same message is transmitted twice. We have also a packet counter incremented with each new transmission, the direction and the barrier identity. Certain signaling messages are exchanged between terminal and the eNode B. Other messages pass through the eNode B, but are exchanged between the terminal and the MME. The integrity mechanisms are implemented in the mobile terminal, the eNode B and the MME. There are three standardized algorithms to ensure integrity that follow the same logic, the ciphering algorithm. Null for the test phase, Snow 3G for compatibility with 3G, and AES. Let's see how ciphering and integrity control are combined. For a given session, we have one constant encryption key and one constant integrity key, starting with the packet. The sender first ciphers it and then adds the calculated MAC code. The receiver does the opposite. Verify the correspondence of the MAC code, then decipher it. To summarize, integrity control is provided for signaling messages in 4G networks. A short authentication code called MAC is added to each message. This code is computed by both the sender and the receiver with an integrity key generated with the secret key and the RAND used for the authentication. integrity is considered as guaranteed if both codes are the same. Key hierarchy. Previously, we saw that we need several separate keys that must be distributed in various elements of the LTE networks for deciphering and integrity algorithm. Now, we'll see how these keys are generated and how they are distributed in the network. We should remember that all the security of 4G networks rests on the principle that there is one single secret shared between HSS and the SIM card. This secret key must never leave these two entities. Yet, we need the first key to ensure the ciphering of user data between the user equipment and the eNode B. The second key to cipher signaling data on the same link, and a third key to cipher messages between user equipment and the MME. To ensure that integrity of signaling messages, we need a key to protect the exchanges between the user equipment and the eNode B, and a second key between the user equipment and the MME. That's a lot more than our shared secret key, and it means it's necessary to distribute these keys to several nodes in the network. Thanks to signaling protocols between SIM, the mobile terminal, the MME, the HSS, the network and the terminal will generate all the keys necessary from the shared secret key, which never leaves the HSS or the SIM card. Because generating all the requested keys requires the use of or knowledge of the secret key, we could think that it would be the HSS which generates and distributes them itself. This will pose a scalability problem. There are several tens of millions user equipment. With each change of an eNode B or of an MME, the HSS will have to be connected to generate new keys. To avoid that, the HSS delegates the generation of keys to the MME that manages the user equipment. If the subscriber is abroad, that MME is in a different network to the one of the HSS. During the first exchanges, the HSS generates a key called KASME, where ASME stands for Access Security Management Entity. This key is then sent to the MME, responsible for the mobile terminal. It's this key that enables the MME to generate the rest of the keys necessary. Nevertheless, the subscriber's HSS only gives its trust to the network that's just contacted it. We want to avoid a situation where the subscriber can be transferred to another network without explicit authorization. That's why the HSS generates the KASME key, taking the identity of the network asking for the key into account. Just note that this network is the visited network. The identity of an operator, as we've already seen, is defined by the MCC or MCC-MNC pair. This makes it impossible for another mobile network to use this KASME key. If the subscriber wants to use another network, it will necessarily be after the explicit authorization of his own HSS. After the exchanges with the mobile terminal, the MME generates another key, the eNode B, based on the KASME key. It's this key that is given to the current eNode B as for the mobile terminal. The SIM card generates the to which the mobile terminal is attaching KASME key, which it passes to the mobile terminal itself, which then deduces the eNode B key. The KASME and the eNode B keys are not used directly to protect exchanges. They are used as the base to generate the set of keys necessary for the integrity and ciphering of exchanges. Several keys are generated from the K-ASME key, the encryption key, and the key from integrity between the MME and the mobile terminal. The abbreviation NAS, which means non-access chatroom, indicates that these keys are between the mobile terminal and the MME. Next, the protection of signaling messages between the mobile terminal and the eNodeB, ciphering and integrity, as well as the encryption key for user data. The abbreviation RRC indicates that these keys are for signaling between the mobile terminal and the eNodeB, while the abbreviation UP, which means user plane, indicates that these keys are for the user packets. We'll see in the rest of the course what these abbreviations stand for. But what is the mechanism with which we can derive these keys and build up such a hierarchy? This hierarchy of keys is built on an ingenious use of cryptographic hash functions. A function like this takes as parameters a secret key and the data to produce the result. Because the output is of a fixed size, and thanks to the properties of cryptographic hash functions, the output itself can be treated like a key. Then, the K-ASME key is calculated using the secret key, taking as input the random number rand, identifying the operator and SQ1 number, the sequence number. In turn, the K-ASME key is used as a shared secret to generate the K-eNodeB key, and so on to guarantee the entire hierarchy which protects exchanges between the terminal and the network. Temporary identity. Could someone track my movements by listening to signaling exchanges on the radio channel? That's the question we'll answer in this part of the video. The IMSI is a permanent identifier unique in the world. As we already saw, before each communication, the mobile terminal authenticates itself to the network. You may recall ciphering is not activated during the first exchanges, and if it used the IMSI for identification systematically, it would be very simple for someone to track our movements. The solution consists in putting in place a mechanism that limits the use of the IMSI to a strict minimum. During the first authentication, the terminal has no other choice but to use the IMSI. On the other hand, once authentication has succeeded and encryption of the radio link has been activated, the network allocates a temporary identifier which is used afterwards systematically. This temporary identifier is called TMSI, or Temporary Mobile Subscriber Identity. Because the TMSI is only allocated once encryption is activated, it is impossible for an attacker to make the link between it and the subscriber's IMSI. The TMSI will be used as identifier for all further communications, guaranteeing that an attacker will no longer be able to identify the subscriber. The TMSI is independently allocated by the mobile terminal's current MME. It can be changed more frequently or less frequently, depending on the operator's policies. It can be kept as long as the user equipment stays in the same cell, or changed each time the user equipment starts a new conversation. It changes with each MME change. The TMSI is a very short identifier, 4 bytes with a local significance for our MME. The same value can be used by 2 MMEs for 2 different user equipments. Therefore, a large identification structure is needed with global significance. The structure is called the GUT, Globally Unique Temporary Identity. It enables the network to locate the MME and allocate the TIMSI. This is the structure of the GUTI. The GUTI contains the TIMSI as well as the unique identifier of the MME which allocated the TIMSI. This identifier is made up of the identity of the operator, the MCC-MNC pair, and NMME code allocated by the operator. More precisely, the MMEs work as a group. We have an MME group identity, group ID, and NMME code beginning to the group. At all times, a GUTI identifies a subscriber in a unique way to the world, while retaining the possibility of changing a subscriber's GUTI. Just as authors or singers, like Agatha Christie and Lady Gaga for example, use pseudonyms, the GUTI is like the pseudonym of the user equipment. However, unlike authors or singers who tend to keep the same pseudonym throughout their lives, here, pseudonym is often changed. When the terminal makes a new request, for example, when it attaches to the network, it sends the first message using the GUTI as identifier. The MME is the only one that can make the correspondence and find the subscriber's IMSI and find the security context. That way, it can verify the integrity of the message. That serves as proof that the mobile terminal is what it claims to be and it is authenticated. The MME can activate ciphering on the radio link, configure the necessary keys on the eNode B, and thereby protect all communications from the first transmitted message on. It is important to note here that the HSS is not connected during this procedure, which limits the load of this central network point significantly. This procedure also functions if the mobile terminal moves. If the terminal is covered by a new MME, it's the new MME that receives the authentication request. By looking at the GUTI, it can find the identity of the former MME, the one that assigned the TIMSI. It can relay the message and, after its validation, recuperate the IMSI of the subscriber together with a security context. Therefore, the new MME can also activate ciphering and integrity without going through a complete authentication cycle. Again, this avoids contacting the HSS. To prevent a hacker from tracking the location of a user equipment, a temporary identity called TIMSI is allocated to the user equipment. The TIMSI is chosen by the MME that controls the user equipment and is transferred only after activation of ciphering. The TIMSI can be frequently renewed. The TIMSI is used to build a globally unique temporary identity called GUTI. Using the GUTI is necessary to recover the IMSI of the user equipment in case of change of MME. Revisiting attachment. How are the different security procedures executed during the attachment? In this part of the video, we'll take another look at how the very first attachment procedures work, but in more details. First, the terminal sends an attachment request to the network in which it includes the subscriber's IMSI and its capacities in terms of security. After receiving this request, the MME needs an authentication vector to authenticate the terminal. It sends a request to the HSS indicating the subscriber's IMSI and the network to which it wants to attach. The network is identified by the country code MCC and by the operator code MNC. If the subscriber is in his network, the country and operator codes are the same as those in the IMSI. If the subscriber is abroad, the MCC and the MNC are those of the visited network. The HSS generates several authentication vectors and sends them to the MME. The MME uses one of these vectors. It begins the authentication procedure of the terminal. The terminal authenticates the network thanks to the authentication token, UTRAN, and sends the response RES. The MME verifies that the RES sent corresponds to the XRES that it has in its authentication vector. Once the authentication is finalized, the MME calculates several keys: keyness enc, keyness int, for ciphering and integrity k enode. The network and mobile terminal then exchange several messages to correctly activate ciphering and integrity. The procedures are designed to avoid ending up in problematic situations where one side is ciphering messages with one algorithm and the other side is receiving them without trying to decipher. The MME activates ciphering of the terminal with security module command. It indicates the encryption and integrity algorithms to use for the rest of communications with the MME. Just note that this message is not ciphered. Following this command, the terminal activates ciphering and data integrity with the indicated algorithms. It responds to the MME, and this time, the response is ciphered and signed. It includes a MAC, Message Authentication Code. The MME allocates necessary resources between P gateway and the S gateway so that the SGW can relay the user data. Then, the MME sends a message to the eNode B to let it know that the user has been authenticated and to give, among the other things, the key eNode B key. The eNode B calculates the integrity key, KRRC int, and the encryption key, KRRC enc. It activates encryption of the radio channel in the same way that the MME activated encryption between itself and the terminal. The eNode B sends the security mode command with the encryption and integrity algorithms to use on the radio channel, which can be different from algorithms chosen by the MME. Once again, this first message is signed but not ciphered. However, the confirmation security mode complete is ciphered and signed. Finally, how is the mobile terminal IP address allocated? After the terminal's response, which activates ciphering between it and the MME takes care of choosing the S gateway and the P gateway. The MME asks the HSS to give the subscriber profile. The HSS answers also and gives the subscriber's connectivity parameters. The main parameter is the APN, which means access point name, which allocates the symbolic name of the P gateway. The MME selects the P gateway and sends a message to it. The S gateway contacts the P gateway identified. The P gateway allocates an IP address. The response is transmitted from the S gateway to the MME. The MME then sends this information to the mobile terminal via the eNode B. From this moment, the mobile terminal can communicate with the rest of the world. Thanks for watching, and don't forget to like, subscribe, and share. Don't forget, 30 days free for the 1,000 first people to subscribe to Skillshare using my link.